Okie dokie. Can you hear me? Awesome. All right. So this week we were talking about min and max type stuff and discussing mean value theorem and like inflection points and that type of stuff. So we're really getting into how can we like apply what we've learned about derivatives. So let's just kind of jump in. So I think we should start in section 3.1 with problem 3. Here we have a graph. It looks something akin to this. This is not going to be perfect, but it's going to kind of give us the right idea. Goes down and then up, and then down, and then up. And we have several points along this graph, including here, which is A, here B, C, D, this is R, and this is S. So this is our x-axis, and this is our y-axis. So for each of these points, state whether the function has an absolute minimum, an absolute maximum, a local minimum, a local maximum, or neither a min or a max. Let's start with A. What are you thinking about A? Local, is there an absolute min or max there? Yeah, it's neither. And is there a local min or max? At A? At B, yes, there's a local min. At A, there is neither because it is one of our endpoints, and so we can't call it like a max. So this is neither. This is going to be a local min. What about C? Local or absolute? What about D? D is partway down between C and R. It is neither. To me, D looks to be located approximately where we move from concave down to concave up. What might D be if it is at that point? Like, what's the name for that point? This is a little bit of 3.3, but yes. It looks like it might be the inflection point. What about R? Yes, here's our absolute min. And S, which this final endpoint here is it can actually. So the idea of the max. So the idea is the reason we evaluate the endpoints. The endpoints can never be like a local min or max because we define like a local max as the rate of change is positive and then the rate of change becomes negative, right? So we can identify where a local max is by identifying, is the derivative at this point 0? Yes. And then we see how the derivative around it behaves. we don't have the information about a derivative outside of the function cutoff essentially. So the reason that we evaluate the endpoints is to determine if they are an absolute maximum, not if they are a local. Does that kind of make sense? Awesome. Okay. Let's do, pretty much nailed that. Let's do number 7, which is kind of a little bit of the inverse of this. So now we are given some statements. It tells us that we have an absolute max at x is equal to 5. We have an absolute min at x is equal to 2. We have a local max at x is equal to 3. And we have 2 local mins. One at x is equal to 2 and one at x is equal to 4. Okay, and then this whole function is going to be on the interval 1 to 5. So, what are some things that you notice about this, or what maybe should I start by drawing? I'm going to say that this, instead of being 0, this is going to be 1. And over here is going to be 5. Yes. Well, that's actually the absolute minimum, right? So it's the absolute minimum and the local minimum. So in this case, our absolute minimum is not going to be one of our endpoints. It's going to be here at 2. I'm just going to kind of arbitrarily put this here. All we need to do is sketch a graph that does fulfill these properties, essentially. What do we have at 3? We have a max, a local max. So I'm going to put it right here. And then at 4, I have another local minimum. Do I need to put this below at a smaller or above at a higher y value than x is equal to 2? Above, exactly. Because it is going to be a local min and not the absolute min. And the same type of question for x is equal to 5. Where does this y value belong? Does it belong below my x is equal to 3 or above? Above, exactly. Okay, and my final question is, what am I doing at x is equal to 1? Where does this belong? Yes, essentially, it can be anywhere between my x is equal to 2 and my x is equal to 5. So I'm going to put it right here because it can be anywhere in this area. And then we can kind of put this all together, and we can see that we have a min, a local max, a local min, and then we go up all the way up here, and we've got our absolute max at x is equal to 5. So that's kind of how you want to start putting this type of stuff together. Let's do some actual problems where we have to find critical points and use those to find mins and maxes. Okay. So, start with problem 30. Here we have the function f of x is equal to x cubed plus 6x squared minus 15x. What is the first thing I should do? Oh, these problems are just asking for the critical points. I think we can go ahead and find what the min and max is at these points. I think that's a fine thing that we can do. So what's my first step? Find the derivative, exactly. So I'm going to take the derivative, and f prime is going to be equal to, I'm just going to use the power rule the whole time here, yep, 3x squared plus 12x minus 15. Yep. All right, so now I have the derivative. What do I need to do with this in order to find the critical points? Exactly. So I'm going to say that f prime of x is equal to 0. And then I'm going to factor out this 3 because I want to make my life just a little bit easier. So this is going to be x squared plus 4x minus 5. So this is 0 is equal to 3 times, what do you think would be a good way to factor this? I know, quadratics. Well, how would you factor this point? Yeah. And then we just want to be sure, so I'm going to go ahead and say that this is x squared plus 5x minus x minus 5, which is exactly what I have up there, so I'm good. What does this tell you? If this, like, basically this phrase is equal to 0, then what must be equal to 0? Well, 3 is equal to 0, which we know can't happen. Which I'm just going to call like a block here. X plus 5 is equal to 0. Or x is equal to negative 5. Or x minus 1 is equal to 0. X is equal to 1. So basically, this is like an either-or situation. Because I'm multiplying all of these numbers together, as long as one of them is equal to 0, then the whole phrase will be equal to 0. So I say that my critical points are going to be at x is equal to 1 and x is equal to minus 5. Because it is at those 2 points where this function has a derivative that is equal to 0. So this problem doesn't specifically ask for us to go ahead and find the min-maxes, but I think that we can go ahead because we've already done most of the legwork here. How would you go ahead and find the mins and maxes now that we have the critical points? Well, we could plug the critical points back into f of x, and that would give us the y value that corresponds to them. But what if I had a function that looked like this? What if my function looked like... So here my max is, this is a max, and it's got a lower y value than this min right here. Now, obviously, this is not exactly what this function looks like, but if we were going based off of, like, this is the lower y value, and this is the higher y value, we would assume that this is actually a maximum and not a minimum. So, did you guys learn how to do the line test? Yes, okay. That's what I would set up here in order to do this. I don't know why it's so small. Small line. So I'm going to set my line test up. I'm going to say, here are my critical points. I have one at -5 and then one at 1. And then I'm going to go through and I'm going to pick numbers that are easy to evaluate. I think it would be easy to evaluate at 0. What would be an easy to evaluate number that's under -5? Be -6. And I'll call that 2. So all I need to do is find out what the sign is of the derivative at these points. And the easy way to do that is to say this is 3 times, so that's a positive number, times x plus 5. So if x is equal to -6, then this is negative. And then -6 minus 1 is negative. So I have a positive times a negative, which turns out to be a positive, which I am actually going to write as an arrow pointing upwards. Come over to 0. I have 3 positive times 0 plus 5 positive times 0 minus 1 negative. Positive times negative is going to be a negative number. Don't care what that number is. I'm just going to represent it as an arrow pointing down. And then over here I have 2. So positive times positive, and then 2 minus 1 is a positive number, so this is going to be positive. And again, I'm going to say this is an arrow pointing up. So the reason I use the arrows instead of just the signs, I'm not sure how you guys were explicitly taught how to do this, but I really like to do the arrows because for me it makes it very clear where the mins and maxes are. So you see we move from an increasing function to a decreasing one. So we have increasing to decreasing. So here we have a max at x is equal to -5. And over here we have a function that is decreasing and then begins to increase. So we have a min at x is equal to 1. So that's kind of how I like to do the line test with the arrows, because it makes it really clear. But we've basically done it. If we wanted to find absolute mins and maxes, we would have to impose some kind of boundary restrictions. We'd have to say, I only care about the function when it goes from -10 to +10. Now, where are my mins and maxes? And in that case, we would go through and we would find the y values for all of the mins, local mins and maxes, and our endpoints and compare in order to find the absolute. But for now, we just kind of care where they are. Okay. Awesome. Let's try something that's maybe not quite straightforward in terms of derivations and that sort of thing. Such as number 38. So here we have the function g of x is equal to the cubed root of 4 minus x squared. So to start with, we have to take the derivative of that, right? How would you take the derivative of that? Yes. So I would go ahead and rewrite this as, this is going to be 4 minus x squared is to the 1/3. And then I'm going to set up my chain rule. I'm going to say my internal function is, I'll call it h of x, which is equal to 4 minus x squared. So h prime of x is equal to minus 2x. And then my outside function is going to be f of h, which is going to be h to the 1/3. And f prime of h is going to be 1/3 h to the minus 2/3, right? Yes. So this is kind of how I've set up my chain rule. I'm going to put this all together so that I have 1/3 times h. So 4 minus x squared. And that is going to be 2 to the minus 2/3 times h prime, which is going to be minus 2x. So this is my g prime of x. So this is going to be equal to minus 2/3x times 4 minus x squared to the negative 2/3. Okay, this is not quite so clean. What are we now looking at? My next step, as we kind of said, is going to be to say that g prime of x is going to be equal to 0, right? So when does this equal 0? Well, I've got some things that are multiplied by one another. So if 2/3 is equal to 0, which it doesn't, and then if x exactly, x is equal to 0, so x is equal to 0. Oh, sorry, I keep trying to erase that one line by undoing, which is not how erasing works. So this cannot equal 0. And then when 4 minus x squared is equal to 0, or rather when 4 minus x squared is minus 2/3, which is when 4 minus x squared is equal to 0, which is when x is equal to what exactly? If I work this out, this is equal to 0, so 4 is equal to x squared, so root 4 is equal to root x. Yes, it's going to be plus or minus 2. Just because we need to make sure that we recognize that minus 2 squared is still 4. So I'm going to erase some of this and write down what our critical points are. Here we're going to have our critical points. Which are x is equal to -2, x is equal to 0, and x is equal to 2. Okay. We've broken that down. And let's go ahead and find out where our local mins and maxes are. So I'm going to go ahead and I'm going to put down where my critical points are, which are going to be at -2, at 0, and at +2. I'm going to go ahead and say this will be -3. I'm going to evaluate it at -1, at 1, and at 3. So for something like this, I might be a little bit more explicit. I'm going to have a negative times x is going to be a negative. And then I'm going to have 4 minus 9 to the minus 2/3. What does that mean? So that is going to be 4 minus 9, which is going to be a negative number. It's going to be minus 5 minus 2/3. Do we have an easy way of telling if that's going to be a positive or a negative number? Well, if we think about it, yes. If we think about it as -5 squared to the third root. Well, rather it's -1 over. This is essentially what we're looking at here. This is not going to make anything negative or positive. It's only this that is going to make something negative or positive. So this may be, you know, like this may seem very complicated, but what we're really looking at is here. And this is going to say that all like products inside are going to be made positive. Just like x squared, right? Is everybody okay with that? Or x to the 4th. Awesome. Okay, so that means that this is going to be positive. For -1, oh, so this is going to be negative times a negative times a positive is going to be positive. Here we have -1, so it's going to be negative times positive. So it's going to be positive. Here we'll have a negative times positive times positive. It's going to be negative. Here we'll have a negative times positive times positive. So where do I have mins and maxes? I have a maximum at 0. What do I have going on everywhere else? The important thing to remember that critical points don't have to be mins or maxes. They can just be points where where the function has a derivative equal to 0. So it might look something like this. I have no idea where this is in terms of scale, but it could just be flat and then up and then down and then flat and then down. So here would be my max at 0, where I transition from a positive to a negative derivative. And then at this point, -2, I go from a positive derivative to a positive derivative, but I still do have a point where my derivative is equal to 0. And the same here at 2, goes negative to negative derivative. Does that kind of make sense? Awesome. Okie doke. Let's do a quick find like absolute max, absolute min problem. And then let's move on to our next couple of sections. Okie doke. So I think a good problem to do, that is, I wrote down one, but I'm rethinking it now. I think we might want to try something a little bit different, just because I think it's good to get practice with trig functions, because they tend to trip people up. This is on the interval 0 to pi over 2. Okay. So now I'm finding absolute min and absolute max. Step 1, derivative. What's the derivative of f of t? Start with 2 cos t. Derivative of 2 cos t. Is this going to be the chain rule? Do we need the chain rule for this? Just for at least this one. Yes, we would use the chain rule for this second term here. But the derivative of 2 cos t is going to be our constant 2, yep, times negative sign. So it'll be 2 sine t. And I see that you added an extra x in there. The important thing to recognize is that we don't actually bring that x out. This is just a constant, this 2 here. And we're just going to multiply it by the derivative of cos t, which is going to be negative sine t. So that's how we end up with negative 2 sine t. And this will be plus this derivative, which is going to be, I'll call it h of t is equal to 2t. H prime of t is equal to 2. Then I'll have g of h is equal to sine h. G prime of h is equal to cos h. And I'll put it together. I have g prime of h, so cos of 2t times h prime, which is 2. So this is going to get put in as plus 2 cos 2t. Okay. So we found our derivative. What is next? Yep, we're going to set it equal to 0. So 0 is equal to, and I can rearrange it a little bit. I'll say this is 2 times cos 2t minus sine t. So this whole thing is equal to 0 when cos 2t minus sine t is equal to 0, which is when sine t is equal to cos 2t, which I got just by adding sine t to both sides. Okay. What does this mean? How can we find this? So what is the difference between cos 2t and a regular cosine? Like graph. What is this 2 going to impact? Is it going to be the amplitude of the graph? You could start thinking that it isn't going to be the amplitude. It's actually going to be the period. So it'll, I believe, have the period. But I think that actually what they might want us to do instead is, I think I jumped the gun a little bit here. I'm going to quick go check my trig identities for cos 2t or cos 2x or whatever, because I think there might be one here. And what do you know? It's a trig identity thing, which is This is not something I'm notoriously good at, remembering my trig identities. It is something that I would definitely recommend you do if you've got the time while studying. If you don't, then like obviously this is not the most critical part of this whole thing. But I'm gonna write this down in a different color. That's a little bit more obvious. Cos 2x is equal to 1 minus 2 sine squared x. So, wondering if we can set up an inequality here. Not an inequality, a quadratic. So this would be 2 times 1 minus 2 sine squared x minus, or sine squared t, minus sine t. Or if we set this up, this would be 2 minus 2 sine squared t minus sine t plus 1, which looks really grody, but if I call it something like minus 2x minus x plus 1, you might actually have a shot at changing this into something that's a little bit more manageable. Okay. I haven't solved this problem yet. I just kind of picked this one because I thought it would be good to get some more practice instead of doing trig problems, instead of the ones that I had actually like picked and practiced. So if anyone has any suggestions here, we're kind of winging it. It's going to be either plus 1, minus 2x squared plus x minus 2x plus 1 minus 2x squared minus x plus 1. That's what we want, right? Eat. Sweet. Okay. So this is, if we think about it in terms of x, that's kind of how we break up the quadratic. So now we're going to write it minus 2 sine t plus 1 times sine t plus 1. So where are we now? We said that 0 was going to have to be equal to 2 cos 2t, 2 times the quantity cos 2t minus sine t. Then we turn cos 2t into 1 minus 2 sine squared t. Then we use the, like the idea of this being a quadratic essentially, to end up with minus 2 sine t plus 1 times sine t plus 1. And so this still has to be equal to 0. So 2 is not going to equal 0. But negative 2 sine t plus 1 can equal 0. And sine t plus 1 can equal 0. So this is going to be, yeah, so this is going to be sine t is equal to negative 1. And that happens at 3 pi over 2 plus or minus 2n pi, right? Sorry. Here we've got a sine curve. It looks like this. It's 2 pi, 6 pi. This is where sine is equal to negative 1. This is where sine is equal to positive 1. Okay. So here's one of our critical points. And then over here, this is going to be where, yes, sorry, I just saw your chat. Yes, so this is going to be sine t is equal to minus 1 over minus 2, so it's going to be 1 over 2. So here I said this was going to be equal to minus 1. Here's where it is equal to minus 1. It is equal to 1/2 at these 2 points, which I believe are pi over 6 and pi over 3. This is a unit circle problem. This is when we have a triangle that looks like this. That is 1, that is 2, and that is root 3. So 1/2 of the opposite of 5 is 1 over 2, so that is pi over 6. Okay. And there should be another point where that is the case. I'm going to go through and circle what we have. Okay. This is what we have right now. There are 2 of the critical points. Sine of t equals 1/2 is going to happen also on the way down. So that's pi over 6. And then we add an additional 2. Is that going to be 5 pi over 6 at that point? Perhaps. So let me, I'm going to go look up a unit circle now. This is a lot more trig than I had anticipated. Whoops. 5 pi over 6. Yep, that's going to be a 1/2. Sweet. Yes, right? That's got to be right. Okay. So we had to use the unit circle and this graph of the sine curve to get here, but we're chugging along. We've got 3 different critical points, right? How many of these are within our interval? 1 of them. Pi over 6. Just plain pi over 6. Okay. So I'm going to erase all of this up to here. Done a lot of work here. Let us see it go. So this is going to be 2 times -2 sine t plus 1 times sine t plus 1. Our critical points are going to be x is equal to pi over 6 plus 2n pi. This basically means it's going to repeat every 2 pi. Our critical points are 5 pi over 6 plus 2n pi and 3 pi over 2 plus 2n pi. And of these, we only care about the one that is within our interval. So I'm going to ignore the other 2 for now. I'm going to set this up so that we can do a quick test, line test. If I have pi over 6 right here, and then I have 0 and pi over 3, this is going to be 2, -2 times sine of 0. What is the sine of 0? Yep. Yep. So sine 0 is going to be equal to 0. So this is going to be 0 plus 1. So we've got a positive times a positive. Sine of 0 again, plus 1, positive. And then sine of pi over 3 should also be positive. Oh. Sine of pi over 3 is, this is pi over 3 in a 30, 60, 90 triangle. So that is 2 root 3 and 1. So it is root 3 over 2, which is positive. So we're going to end up with minus root 3 plus 1. And root 3 is larger than 1, so this is going to be negative. So positive times a negative. And then this is going to be a positive because it's going to be root 3 over 2 plus 1, so positive. So this is going to be negative. Everyone followed me up to here. Awesome. Okay, so where did I lose you? It was probably just that enormous amount of trig junk. Yeah. Trig identities, unit circle, trig graphs, unfortunately, are my biggest, like, oh, this is kind of what I had to use. I had to use all 3 of them in order to get where I am. So I now know that x is equal to pi over 6 is a maximum. All right. What is the last thing I need to do to find my absolute min and my absolute max on this interval? Because for previous problems, it was fine that I just knew that I had a max at this point, but now I want to know what the absolute min and max is. Yes, so I do have a max when x is equal to pi over 6. But how do I tell where the absolute max is? I'm going to need to compare my maximum, like the actual like y value of my maximum, to the actual y values at my endpoints, essentially. How do I do that? How do I compare those y values? We were talking about this earlier. Yes, now is the time to plug them back in to the derivative or to the original equation. Yes. So here we have f of 0 is my first endpoint. And then I'm going to find out what that is equal to. And then I'm going to have f of pi over 6. And then I am going to have f of my second endpoint. And if these were within my interval, I would also include those in here, but since they're not, I don't really care about them. So now I have 2 times cos 0 plus sine 0. I have 2 times cos pi over 6 plus sine, what is this sine of? T, and if my t is pi over 6, then this is, yes, going to be pi over 3. And then I have 2 cos pi over 2 plus sine of what? It's going to be pi. So we said that sine of 0 is equal to 0. What is the sine of pi? Yes. Does anyone know where cosine is going to be equal to 0? Or presumably you're talking about right here. Okay, I'm just getting a series of 1s and 0s, and I kind of asked a series of disjointed questions, so I'm not sure to which these 1s and 0s are referring to. Let's just start at the top now that we've identified where the sine is equal to 0. Is that true? I typically think about this graph for a cosine, draw like this, where I start off here, I go down, and then I come back up. So this is like what a cosine graph looks like. One iteration. This is cos x from x is equal to 0 to x is equal to 2 pi. This is if nobody does anything to my function. So when x is equal to pi, then cos x is equal to -1. And that's kind of how I read this graph, right? So when cos is equal to 0, yes, cos of 0 is going to be 1. Yes, I'm so sorry. I was like thinking of the wrong part of this problem. I'm just being a doofus today. You are correct. So this is going to be 2 times cos 0, which is going to be 1, plus 0, so this is going to be 2. Let's do this down here now. What is going to be cos of 2 pi? Based on this graph that I just kind of gave you, or what you remember of this graph. Yes. Cos of 2 pi is going to be here, or pi over 2, excuse me. Pi over 2 is what's here. Pi over 2 is going to be 0, and this is 3 pi over 2. My brain is apparently applesauce today, and I'm sorry that I keep misreading these, and I hope I'm not confusing you too much. But basically, these are the 5 main points that you should kind of know along a cosine curve. So cosine is cosine of pi over 2 and 3 pi over 2 is equal to 0. Cosine of pi is going to be equal to -1. And then as we established, cosine of 0 and cosine of 2 pi is going to be equal to 1. So this is going to be 2 times 0 plus 0. So this is going to be equal to 0. I'm going to erase this curve right now so that I can think about this. Instead of dealing with a curve, I think it would be easiest to deal with a triangle now. So this is the smaller one is pi over 6, and then this larger one is going to be pi over 3. This is going to be 2, this is going to be 1, and this is going to be root 3. And this triangle, this 30, 60, 90 triangle is how we're going to determine what all of these are equal to. So if I have 2 times the cosine of pi over 6. Here is pi over 6. The cosine is the adjacent over the hypotenuse, so it's going to be root 3 over 2. And then I'm going to add to it the sine of pi over 3. Pi over 3 is up here. It is going to be the opposite over the adjacent, or rather opposite over the hypotenuse. So that is going to be root 3 over 2. And this is going to be equal to, we'll call it 3 root 3 over 2. Okay. So I'm going to clean this up just a little bit more so that I can get this in a position where I can use it. So this is 2 here. F of 0 is equal to 2. F of pi over 6 is equal to 3 root 3 over 2. And f of pi over 2 is going to be equal to 0. Based on this, what is my absolute minimum and what is my absolute maximum? Yes. My absolute max is the point pi over 6, 3 root 3 over 2. So here's my x value, and here's my y value. Where is my, yes, and then my absolute minimum is going to be here at pi over 2, 0. Again, that ordered pair. Okay, thoughts, comments, questions, concerns? That took a lot longer than I thought it would, and I'm so sorry for driving you through that, but I hope you kind of learned a couple of strategies maybe for dealing with some of the more complicated trig function type problems. Let's quick move through if you guys don't have any questions and do some stuff in the other sections. Questions? So 3.2, we're talking mean value theorem. The idea here is that there is going to be a point on a very specific type of function that has a slope where its derivative has a slope that is equal to the average rate of change between these 2 points. So let's just do, I think I was going to do number 5. Walk me through number 5 here, where f of x is equal to 2x cubed minus 4x plus 5, and we're on the interval -1 to 3. So we want to verify the function satisfies the 3 hypotheses of Rolle's theorem on the given interval, and then find all numbers C that satisfy the conclusion of Rolle's theorem. So, what are the conditions of Rolle's theorem? So, for Rolle's theorem, f of x must be continuous on the interval a to b. F of x must be differentiable on a to b, and f of a is equal to f of b. So if all of these conditions are met, then there is a number c such that f prime of c is equal to 0. Okay. So basically the idea is that if I have something that's like increasing and then it decreases so that we start and end at the same y value, then there is a point where there is like a critical point where the derivative is equal to 0. So does this function meet Rolle's theorem starting from number 1? Is it continuous on a to b, and how can you tell? Yes, polynomial. Is it differentiable on a to b, and how can you tell? Yes, it is differentiable, and it is going to be, because it's a polynomial, it is going to be differentiable for like all real numbers essentially. There are no like points at which this would not be differentiable. Okay. So now how do I evaluate number 3? My third condition is that f of a is equal to f of b. How would I evaluate that? The easiest method is to just say, here is f, here is a, here is b. So I just need to say that f of -1 is equal to f of 3. That would mean that 2 times -1 cubed minus 4 times -1 plus 5 is going to be equal to 2 times 3 cubed minus 4 times 3 plus 5. This is going to be 2 times -1 cubed is going to be 2 times -1, so that's -2 plus 4 plus 5. Which is equal to 2, that is 27 minus 12 plus 5. That doesn't seem right. Oh, I don't think so. Doesn't seem correct. Oh yes, 27 times 2, yes. Which is going to be far too large, and I'm like 99% certain that this is like valid. So it means that I did something wrong. Not sure what that something is. Give me 2 seconds. I'm going to go back and look at the problem in the book. If I can find it again, which I might not be able to. I just misread the problem. Big oops there. This is squared. So that is squared and that is squared, and everything makes a lot more sense now. So this is going to be, that's going to be 1 now, so this is going to be 2, plus 4 plus 5, and this is going to be 2 times 9 minus 12 plus 5. This is going to be 18 minus 12 plus 5. That'll be 6 plus 5, or 11. And this will be 2 plus 9, or 11. So 11 is equal to 11. We've set ourselves up so that this is true. F of A is indeed equal to F of B. What does this mean that we get to do with this? Now that we've shown that Rawls's theorem is valid, how can we use the mean value theory? Yes. So we're going to say that, we're going to say that f prime of x is going to be equal to 4x minus 4. And f prime of c is equal to 0, which is equal to 4x minus 4. This is going to be 4 times x minus 1. So this is equal to 0 when x is equal to 1. So c is equal to 1. And we only have one instance where this is the case. So I believe that's just what they wanted us to find. Find all numbers c that satisfy the conclusion of Rawls's theorem, which is there is a number c such that the derivative of c is equal to 0. And that is what we found. Okay. I want to do a quick problem from 3.3 before I have to let you guys go. Is everyone feeling okay with Rawls's theorem? Awesome. Okay. So 3 has us doing a lot of stuff with looking at graphs, looking at inflection points, thinking about how graphs kind of are shaped and how they can be drawn, essentially. I think a lot of questions that my calculus professor really liked was essentially giving us a function, like a huge piece of paper and a function, and saying, this is f of x. I need you to find me f prime of x, f double prime of x, find me all of the critical points, find me all of the inflection points. Tell me where my absolute min and absolute max is, where my local min and max is, where my concave up and concave down, and then wrap it all up with draw this graph for me. So those are the types of problems that my calculus professor was a huge fan of, and I think most calculus professors really do like. We are instead going to do number 7, just because we're running a little bit short on time, where we have a function that looks like this, or a little bit like this. And basically, we're going to use this graph to tell where the inflection points are. So I'm going to erase this and redraw it really fast. Basically, and this is going to be okay. So this is 1, 2, 3, 4. This is kind of clumsily drawn. I'm sorry. That is 7, 8, and it continues. basically what they're asking is, if this is the graph f of x, where are my inflection points? Yes, I will have them at 0.3 and 0.5. Because from here to here, I'm going to be concave down. From here to here, I'm going to be concave up. And from here to here, I'll be concave down. So my inflection points will be at x is equal to 3 and x is equal to 5. Awesome. What if this is not f of x? So I know where my inflection points, if it is f of x. What if this is actually, they just gave us f prime of x? How does that change? What are inflection points to f prime of x? Actually, you're thinking about it in the right kind of way. So what if instead, I'm going to skip to the next problem actually. I'm going to say, what if this is f double prime of x? I'm looking at the second derivative. Where, on this, like, what does it mean to be an inflection point? How would I calculate an inflection point? Inflection point is going to be where the second derivative is equal to 0, right? So your answer that you gave for the first derivative is actually going to be applicable here. I drew the graph differently than they did in the book. In the book, this does come down and touch the 0 line here at 4. The way that I drew it, though, it doesn't. So the only 2 points where the double derivative would be equal to 0 are here at x is equal to 1 and x is equal to 7. Does that make sense? Awesome. Okay. And if you look at how it is drawn in the book, x is equal to 4 would be included in there. But I didn't draw it that way because I'm not very good. Okay. Now let's come back to f prime of x. How can we relate to f prime of x to f of x, or f double prime of x, excuse me? So we will be looking for inflection points. What does it look like to go from a position of like an original function to the derivative of that function equaling 0? If we think about it in a simplified way, yes. It'll be akin to going from f of x to f prime of x is equal to 0, which is where the slope of a function, I love the way that you said that, yes, the slope of a function is equal to 0. The slope of f prime of x is equal to 0. That's the point where we're looking for, the points. Where are those points? Where does the slope of the derivative equal 0? Exactly. At our mins and at our maxes. In this case, x is equal to 2, x is equal to 4, x is equal to 6. Awesome. Okay. That's about all I've got for you. Do we have any questions or comments about what we kind of went through this week? All right. Thank you all for coming. I hope you have an excellent weekend, and I hope you have a good week. Thank you again for showing up.